We have a few more mechanical bits to sort out. We do want to point out that I have not told you what the curl of a vector field or the vector curl of a vector field will tell us in terms of a derivative. We have not talked about what the divergence of a vector field is going to tell us about the vector field. We do at least know the gradient of a scalar function. We know what that tells us, but we still need to learn what the curl and the divergence are telling us about this vector field. But we have seen this the curl and divergence in terms of this del operator. And in the structure of the fundamental theorem of calculus, that's our derivative. This del operator is acting as our derivative. In the case of the fundamental theorem of calculus for line integrals, we evaluate the potential function at the boundary. In the case of Stokes' theorem, we evaluate the vector field along the one-dimensional boundary of the surface. And in the case of the divergence theorem, we evaluate the vector field at the surface of the solid. All right. So let's get back into the parts and talk about the parts. We know that C is some oriented path between 2 points. So C was a one-dimensional path from P to Q, and dr was the direction along that path. Dr is a vector tangent to the path. So we have some path. From P to Q. And then dr is just the direction of the path at a given point. So at some point, dr is just tangent to the path, is some tangent, some vector tangent to the path. This curve is sitting inside some vector field, and we're looking at the interaction between the vector field and the direction along the path. What is the vector field doing to our path at this point? This is what we needed in a line integral. But in Stokes' theorem and in the divergence theorem, we don't just have, in Stokes' theorem, we have a line integral on one side where we're evaluating the function at the boundary. On the other side, we have a surface integral. So we got to think about what this, when we have a surface, what is this dA on the surface? When we were talking about line integrals, dr, everything fit together. Dr was just tangent to the path, because we want to know what the vector field is doing in that direction. How is the vector field augmenting our path? But now we've got a two-dimensional surface S that's showing up in these surface integrals. We're integrating a vector field over a surface. Presumably, dA is some piece of the surface, but it's got to be a vector. It's not just going to be a dx times dy like we had in a region. dA is a vector quantity on the surface. So if we imagine a surface, we can't have dA be just a piece, we can't have dA be tangent to the surface like we had with a curve, a one-dimensional curve. Remember that tangent to the surface is going to be a plane. So dA is a vector. So first we want to note that dA is some vector. Our first inclination might be to grab this, do the same thing we did with dr. It shows up in kind of a similar context. We're integrating a surface dot dA instead of dr. In the case of a line, the dr was tangent. Maybe we should go with the tangent, but tangent to a surface is a plane, not a line. We know that we want dA to be a vector. But tangent to a surface is a plane, not a line. So dA can't be a tangent, because there's only one vector. So we've got this surface. Tangent is a plane. We're in R3. What's my next option? I've got a plane, and I'm using the word vector. What vector am I talking about? What's my only option? No, we're all in this together. What's our only option? Can't make a tangent vector because it's a whole ass plane. It's two-dimensional. We're in R3. What's left? Perpendicular. The only option is to make a vector perpendicular to the plane, a normal vector. So 2 dimensions are taken up by a tangent plane. We can describe that whole plane with a normal vector, everything perpendicular to the vector. So for a surface, this dA is going to be a vector perpendicular to the surface, or normal to the surface. If we take R3 and subtract out a plane, we end up with a line that's going to be perpendicular to the plane. So dA is going to be normal to the surface. And everything fits together again. So dA is going to be a vector normal to the surface. So when I have F dot dA, instead of looking at how the vector field is interacting along a curve, so F dot dr along a curve, I'm looking at F dot dA. The vector field interacting with a vector normal to the surface. So I've got this little dA vector normal to the surface. Now remember, the surface is going to be changing continuously, and that's always a mess. It makes our multiplication really messy when one of our factors is continuously variable and our surface is all bent. So what we're going to do is the same thing that we always do in calculus. We're just going to flatten everything out, because if we look close enough, everything is flat on differentiable surfaces. And our surface needs to be differentiable anyway, because I'm taking derivatives and applying them to my surfaces. My del operator has all these derivatives running around. I better have a differentiable surface. And if we have a differentiable surface, if we look close enough, it's always going to be flat. We're close enough to the surface of the Earth that a significant portion of the population believes that the whole thing is just flat. Because if you look close enough, everything's flat. But we need to make one direction out of this a vector, not like the musical group. I'm not familiar with their work, so I couldn't do that anyway. So since tangent to the surface, we're going to flatten out the surface, and we're going to approximate that surface with a little flat piece that's tangent to the surface, because that's the best flat approximation. That's always what your tangent is. Your best flat approximation, be it a line, be it a plane, be it a three-dimensional solid tangent to a four-dimensional object. And we're just going to go perpendicular. dA is a vector perpendicular. Or normal to the surface. At all the points on the surface. Gets back to our other core problem in calculus. Where are we going to put the plus sign? Then limits come along and say, don't worry about it. At each point on the surface, we've also got some vector. And the way we're going to think about it is we're going to think about the vector field flowing through the surface. Oops. So at each point, I'm going to imagine the vector field flowing through the surface. How much of that vector field is flowing through the surface? How much of F in the direction of dA, the surface? And that is our dot product. Just like it was the dot product over here, when at this point, how much of our vector field in the direction of our curve? We haven't thought about what curl of F and divergence of F are telling us about the vector field, because we've got to worry about what this surface integral is. We spent a lot of time worrying about what this line integral is and how we deal with that. Now we've got to deal with this surface integral business. This is the same thing that always happens in math class, because before you got to calculus and you started worrying about what this derivative business was, you had to learn how to evaluate functions at points. And that's what we're doing now. We're thinking about not just plugging in points and subtracting. We're thinking about, what is this business? What is this line integral telling us? It's how much the vector field is interacting with this one-dimensional curve. It's how much the vector field is interacting with this two-dimensional surface. Since we're using a dot product, any applications of the dot product are going to be applications of our line integrals and our surface integrals, which are also called flux integrals. Flux being flow. So flow integrals. And that's why we kind of cast this as the vector field flowing through the surface. So we've got some surface, and we've got vectors that are normal to that surface. So I'm going to just use this surface. And then at each point, we have the vector field flowing at in different directions through the surface. So maybe at this point, it's flowing in the exact same direction, right at the camera. I need to get a 3D camera. 3D movies went away pretty fast again, didn't they? This always happens. 3D movies have been around like 3 different times. Like first with like the red and the blue. And it's like, oh, well, looking at the movie through the red and the blue makes the movie look really crappy because the colors are stupid. But, you know, like 3D. And everybody's like, oh, this is what movies are going to be from now on. 3-dimensional. And then we're like, oh, no, that's not going to happen. Then it comes back. And it's like Friday the 13th, part 3. Now you don't have to have red and blue. And so it's like, oh, look, he's stabbing us. Ah. And it was like, oh, now we've got it. This is what movies are going to be from now on. And then we're like, oh, no. Then we went even so far as to put this friggin' stuff in people's homes. Here's a television. Here's some glasses. Now you can have 3D at home. And it's like, all right, now this is where it's at. I don't remember what year that was because 3D always goes away. So anyway, it's fun when you're watching a movie on your regular television and it came out in the theaters in 3D. And you can tell because there's always some goofy shit flying at the screen. It's like, whoa! And it's just like, that doesn't work anymore. You know what I mean? Everybody thinks it's going to be like, oh, we're going to visually stun people. No one has been visually stunned by a movie since Jurassic Park. Jurassic Park was the end of visuals. Not because it was like the best ever or anything like that, but people were thinking, how did they breed dinosaurs? I know that the dinosaurs aren't real, but my brain is certainly not convinced of that. And that was in 1993. I think that was the last time I will be visually amazed by a movie. You know what I mean? People talked about Avatar. No. You were more impressed with the world building than the visuals. And the world building was terrible. It just looked cool. Do you know what I mean? Now movies are like, there's too much stuff going on in movies. It's like, oh, I have a MacBook Pro. And that's like, you can do that shit at home. But back in 1993, all you had to do was to advertise the next greatest movie of all time was to say, Spielberg's making a dinosaur movie. You didn't show any trailers. You just said, summer 1993, Spielberg, dinosaurs, be there. And everybody's like, oh, fuck yeah, we're going to be there. And we were all like blown away visually by the shit that happened to us in that movie. Now, I think it's over. Anyway, what were we talking about? Oh, yes, that's right. So at some points, the vector field is going to be flowing perpendicular or normal to the surface. So it's like all flowing through the surface. But in other places, the vector field is going to be flowing at some wacky angle. And I'm going to want to know how much of this vector is going in the direction normal to the surface. How much of this vector at this weirdo angle is perpendicular to the surface. And that's what the dot product is telling us. It's the same calculation that we were making when we had the vector field at each of the points on this curve. We're not doing anything new. We're just spreading it out over a surface. And instead of tangent, we're looking at normal. I told you at the beginning of this class that Calc 3 was the easiest part of calculus because it's all the same stuff. We just had to upgrade multiplication to dot product. Now, anytime we have a dot product, we have an application. Anytime we have a dot product and quantities that can be spread out over a surface or along a one-dimensional curve, we have an application for line integrals, and we have an application for flux integrals. And we have an overall structure for what we're doing. Any questions? How's everybody okay? At this point, you're going to observe that I still have not told you what the curl of a vector field is or the divergence of a vector field is. We've just talked about the structure with this derivative. We've talked about what a surface integral looks like in the calculation, but I haven't told you what curl and divergence is. And so you might be thinking, well, there's a lot of time left in class today. Are you going to tell us what curl and divergence is? Michael, let's talk about curl and divergence so we can get a better understanding of what's going on tomorrow. That's going to do it for today. I know it's super early, but I want this in your mind today. I can't just pile on more shit and expect it to land. I need this to land right now. And then we can start talking about curl and divergence. Still structure, then decoration. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.